everyone. Good morning. It's a pleasure to introduce Professor Roberto Maiolino today, who kindly accepted to give a colloquium with such a big audience, for the first time. And so he asked me to keep the introduction brief, although this is quite a challenge because he has done many things and he works on basically everything related to extragalactic astronomy. So I'll try to summarize, but I have to say a few things because this is a colloquium. And for those of you who doesn't know him, he's a Royal Society Research Professor at the Cavendish Laboratory of the University of Cambridge, and also at the Kavli Institute for Cosmology of the same university. He has been director of the latter institution since 2016. And a brief overview about his trajectory. He did the PhD in Florence, then he was a postdoc at the Max Planck in Garching. Then he became astronomer at the Astrophysical Observatory in Florence. And then he was senior astronomer at the Astronomical Observatory of Rome. And then he moved to Cambridge. In 2019, he was appointed honorary professor at the University College of London. And like I said, he works in basically everything that has to do with extragalactic astronomy, but in particular, he has a significant number of works in the field of galaxy formation and black hole coevolution. And in the recent years, he has also focused on the investigation of the chemical evolution of galaxies and of intergalactic medium. He exploits data from multiple observatories, for example, the BSC and ALMA, but not only those. And he's member of the instrument science team of NIRSPEC, the Near Infrared Multi-Object Spectrograph for the James Webb, who is going to apply very soon. He's the project scientist and the co-PI of MOONS, the Object Near Infrared Spectrograph for the BSC. And he's the project scientist of HIRES, the high resolution spectrograph for the ELT. And apart from all this, he also found the time for writing a book. And if you are interested, it's called Stars and Waves, and I'm actually going to read it myself. So Roberto, the floor is yours, and thank you so much for
Thank you, Christina and Ignacio, for inviting me. This was supposed to be longer visit, which because of the situation was downsized to 1 week, but I hope that I can visit again a longer period next year. And I think this is my very first seminar in person, I think, after the pandemic or during the pandemic, I don't know. All right, so yeah, when I give so the title of the seminar that I decided to give was multiple routes of galaxy transformation in galaxies. And when I first sent this title, I thought I had in mind a broader range of galaxy transformations, but I realized that would be actually too much. So actually, I will focus only on one kind of transformation, that is from star-forming galaxies to passive galaxies, and it will be most of the focus of the presentation. Can you all hear me probably with the mask? Okay. And sorry if sometimes I get hazy because my glasses. Okay. Right. So we know that. Is it possible to dim a little bit the front light or not? So we know that. Galaxies. That's fine. Well, I don't want people to fall asleep because obviously. So maybe maybe it's fine with it's better. Yeah. So yeah, we know that galaxies form stars across the cosmic epochs with a peak of star formation around redshift 2. And so during this time, they form stars in galaxies, but eventually only about 7% of the baryons make into stars. Okay, so the star formation process has been very inefficient across the cosmic epochs, across more than 13 billion years. So the question is why this has happened. And we understand now that in recent years, the focus has been not rather to understand how stars form in galaxies, but actually why stars do not form in galaxies. It becomes an even more interesting question. Okay? So we know that galaxies form as a consequence of gravitational collapse and accretion of gas and cooling in dark matter halos. And this process, the way that stars form in these dark matter halos, is not, it doesn't have the same efficiencies in all kind of halos. And this is illustrated by this kind of diagram, which many people know very well, which shows the mass function of dark matter halos and the mass function of stellar mass in galaxies. And you see that if star formation in all dark matter halos was the same for all of them, these two lines should have the same shape and just scaled down. Okay, instead the shape is completely different, which is telling you that the star formation overall is much more inefficient in massive halos and in low mass halos. And there have been suggestions that generally that this is due to feedback of supernova, and here feedback from black hole accretion. And I will show you that this is actually a somewhat naive first order approximation. This global inefficiency of star formation in dark matter halos, in the end, often is tightly linked to the so-called galaxy bimodality. And what I'm going to say will be horrifying for most of people in the extragalactic area, but galaxies can broadly be divided into two main classes. Okay, one are the star-forming galaxies, which are rich in gas with young stellar populations, and then we have the population of passive quiescent galaxies, which have little gas content and much older, therefore redder population. And the key question is why at some point some galaxies decide to stop forming stars and they are transformed into passive systems. So what is called the quenching mechanism which quench star formation in galaxies. And to make this question a bit more quantitative, people often refer to this diagram, which shows the star formation rate in galaxies as a function of stellar mass. And what you see here in contours and color is actually the distribution of hundreds of thousands of galaxies from the Sloan survey. And you see that most star-forming galaxies essentially distributed along this region, which is improperly called, if you want, the star formation main sequence, where the star formation rate is nearly proportional to the stellar mass in galaxies. But then you have another population of galaxies, which are, for the same stellar mass, are much more quiescent in terms of star formation. And actually, most of these are upper limits in the sense that you don't really actually get any star formation in the system. So the question is, again, why at some point galaxies up here decide to stop forming stars and transit to the quiescent region. Now, trying to understand why galaxies form or do not form stars, in the end translates into understanding their gas content, because we know that stars form out of gas, gravitational collapse of molecular clouds, and this is very well illustrated by the so-called Schmidt-Kenkat relation, which relates the star formation rate surface density to the cold gas surface density, okay? And essentially is telling again that stars form out of gas, and the more gas you have, the more stars you form. So you understand that understanding again why galaxies form or do not form stars translates into understanding how much gas they have and how efficient is this gas in forming stars. So having said that, clearly you have two possible ways of quenching star formation in galaxies. Okay? One is simply to reduce the amount of gas in galaxies. So if you reduce the amount of gas via the Schmidt-Kenkat, you also reduce the amount of star formation. That's easy. And then you have another way, that is you go vertical, that is you keep the amount of gas unchanged, but you reduce greatly the efficiency with which this gas from stars. Okay, so you move this way. So the question is to understand which of these two mechanisms is primarily responsible, and why this mechanism, why this happens. Okay, and the important thing to understand, however, is that the amount of gas in galaxies is not a fixed quantity. Galaxies are not isolated. They keep accreting gas from the intergalactic and circumgalactic medium. And this is illustrated nicely by this Eagle simulation, where you have the dark matter halo here and the dark matter filaments connecting the halo on the left. And here you have the gas distribution. And you see that through the these dark matter filaments, gas has been accreted onto the central galaxies, which is then distributed in a disk, and is where stars start forming. So where you start developing the galaxy. So you have this continuous process of gas accretion, and therefore which keep replenishing the galaxy of gas available for fueling additional star formation. Now, this is a cosmological simulation, but we do see gas accretion in observations. In the case of our Milky Way, the best evidence is probably the famous H1 high velocity clouds, which are clouds of gas orbiting around the galaxy, and some of which are accreting onto the galactic disk. Okay, but the evidence for accretion in other galaxies has also been known for a long time through the imaging of atomic gas with 21 centimeter mapping in nearby in other galaxies, and finding large clumps of gas in the process of accreting of the galaxy. And there have been also other methodologies, more direct or indirect, as we have been discussing this morning a lot with, for instance, by using metallicity traces. So the question now of understanding how to suppress or quench star formation in galaxies essentially translate in figuring out one of these three scenarios. So you can quench or suppress star formation in galaxies by removing gas. You remove the fuel for star formation, and you can do that, for instance, through ejection, so via outflows, or via ramp pressure stripping. Or you can stop the inflow of gas, the accretion of gas onto galaxies. And if you do that, you don't immediately suddenly stop the formation. The galaxies still keep using the available gas for forming additional stars. And then when that gas is totally used up by star formation, this galaxy simply die by starvation, you say. Okay, this is the so-called starvation scenario. Alternatively, as I mentioned, you can have that the gas amount is more or less unaffected, and simply the available gas is made inefficient in forming stars, for instance, by stirring or turbulence, heating, and so on. Okay, so I will go through these three scenarios and see which of them might be the dominant process in quenching. Okay, so let's start with the first one, which is more commonly referred to as the ejective scenario, ejective mode. One of the obvious way to eject gas from galaxies is via galactic winds, galactic outflows, and we know that these are nearly ubiquitous. For instance, in highly star-forming galaxies, the so-called starburst galaxies. This is an image of beautiful images of M82, the prototype of starburst galaxy, where the piling up of the energy injected by multiple supernovae combine to produce these massive outflows which eject gas out of the galaxy. However, the question is whether this outflow is really so disruptive for the galaxy. If you look at this simulation by my colleagues in Cambridge, what you see here is a galactic disk where on the top panels you see face on, and the bottom panels is in edge on. And on the left, the density and of the gas, and the right, the temperature. And what you see all of this flickering here are all the supernova explosions, okay? And you see that at some point when the supernova explosions combine together, at some point they team up to produce a massive outflow in a very hot outflow of the galaxy. Well, this is certainly a very harassing for the galaxies, very damaging for the galaxies. But you see that in terms of gases, you see all of these holes that appear in the gas, which actually produce are regions where the gas is being ejected. But overall, most of the gas remains unaffected in the galaxy, which means that according to simulation, in the end, most of the energy injected by supernovae leave the galaxy along the least resistant paths that is perpendicular to this, and leave most of the gas in the galaxy unaffected. So it doesn't seem that these starburst-driven outflows are particularly damaging for the galaxy. And you see this actually in observation. We now detect galactic outflows driven by star formation in many galaxies, both locally and with the highest redshift. This is probably the highest redshift evidence of massive outflows in the starburst galaxy redshift 5.6, which we have obtained with ALMA data. And you see here, you have this diagram where you have the outflow rate, and which is dominated by the molecular phase, and this is the star formation rate. And you should focus now on the stars, which are the star-forming galaxies. And you see that the outflow rate is actually of the same order, if not lower than the star formation rate. So the rate at which gas is ejected out of galaxies by these galactic outflows is comparable with the star formation rate. So it's not particularly damaging. And you may see that this extreme starburst galaxy, which you may see is the most where the outflows are most, how to say, damaging, which is actually this case here, actually has an outflow rate which is an order of magnitude lower than the star formation rate. Okay. However, if you have an accreting black hole, then this can actually be much more damaging for the galaxy. Indeed, so what we call the active galactic nuclei phase, or AGNs, or quasar. Indeed, if you compute the energy injected into the galaxy by the accretion to supermassive black hole, by assuming a reasonable efficiency in which gravitational energy is converted into radiation, and you compare it with the gravitational binding energy of the galaxy, you get that this ratio is of the order of 100, okay, which is huge. Okay, so potentially accretion to the black hole can be completely devastating for the galaxy, can totally unbind the entire galaxy. Of course, that doesn't happen. Why? Because the coupling between the radiation injected, the energy injected by the quasar, by the accreting black hole, and the ASM of the galaxy is not high. But even so, you understand that even if this coupling is only a few percent, the effect can be actually quite devastating. Okay, and we do see quasar-driven or AGN-driven outflows now in many galaxies. And Christina has been leading this area with various works on, especially in quasar kind of galaxies, but all kinds of galaxies, I would say. And you see here an example of ionized outflow in a nearby AGN traced with the optical nebula lines, particularly CN3, in this nearby super galaxy. And about 10 years ago, we obtained the first discovery of the molecular phase of these quasar-driven outflows, the detection of very broad wings, of very high velocity wings of the CO transitions. And these actually turns out to be where the bulk of the mass in outflows typically is. In this case, we infer outflow rays up to 1,000 solar masses per year, which is huge. Really, these quasars are capable of driving us out of galaxy like crazy. And now quasar-driven outflows are detected in out to very high redshift, especially again in these cold phases, with again outflow rates which are thousands of solar masses per year. So these quasar-driven outflows can be really potentially damaging. And you see this in the same diagram that I showed a few minutes ago, where now I'm highlighting the AGNs or quasars, and you see that in some cases the outflow rate can be 1 or 2 orders of magnitude higher than the star formation rate. Can be really the major player in this quenching business. However, it's also true that for a large number of AGNs, despite having the spacer-driven outflows, the outflow rate is not, again, significantly higher than submission rate. So it can be quite devastating for a number of AGNs, but not for all of them. And as I mentioned, another way to remove gas galaxies is the so-called run pressure stripping, and this is particularly relevant in regions where you have very dense circumgalactic or intracluster gas, in this case placed by X-rays, and this has galaxies plunge into the halo of a massive galaxy or a cluster. Is the run pressure stripping just remove most of the certainly the gas in the outskirts, but in some cases this effect is so strong that it moves the bulk of the gas. And Ignacio has, you certainly know that has also highlighted earlier this year that this effect that can actually is not a simple effect of environment, can be modulated by the AGN in the central galaxy, which essentially is responsible for shaping the distribution of gas in the circumgalactic medium, and therefore modulating this effect of run pressure stripping. So you see that the scenario is actually even more complicated. Okay. Now let's now explore the starvation scenario, which is sometimes called preventive or delayed mode. And I understand why this case is called delayed, because the shutting down of star formation is not sudden, as in the case of outflows, is a delayed effect when you stop the supply of fresh gas. Now, historically, the first cases where this was identified are radio galaxies and their intercluster or circumgalactic medium around massive galaxies which eject radio jets. And the point here is that around these massive galaxies, typically at the center of clusters, you have a lot of a huge amount of gas, which is cooling very rapidly through X-ray, and you see this in the X-rays. And if there was no heating, this gas would cool very rapidly and accrete on the center of galaxies on very short time scales, boosting a lot of star formation in the center of galaxy. And this is not happening. We see that the center of galaxy is relatively, maybe not quiescent, but actually has a very low star formation rate. And so this is happening because the gas in the halo is being continuously heated by injection of energy by the central red gas to its accreting black holes, which produce radio jets, which inject energy into the circumgalactic and the intracluster medium. And you see this nicely in this diagram, which shows the energy injected by the radio jets as a function of power cooling in the observed X-rays, and the two of them are nearly equal. So that is, you have as much cooling as heating. It is the two of them are in nice balance. Honestly, when this was proposed, this was already long ago, 10, 20 years ago, I was, as many colleagues, very skeptical about this, because how it can be that with the radio jet, which is a very collimated thing, you can heat an entire halo which is cooling. For me, it was like if you want to heat the entire AC, it doesn't make any difference if you have a fire in a room or you distribute the heaters across the entire building. So it was totally something I couldn't really understand. But I changed my mind when I saw these fantastic images. And these are essentially the same X-ray images that I showed in the previous slide, but where the diffuse emission has been removed and has highlighted the sharp features by energy detection algorithm. And you see that now there is this plenty of sound waves which are essentially propagated across the entire intercluster medium. So what's happening is that although the jets are very collimated and directional, anisotropic, in the end, these sound waves manage to propagate this energy across the entire halo. So in the end, the heating is actually happens across the entire halo. So this is clearly how these halos are heated and kept preventing from accreting onto the galaxy. Of course, radio galaxy in which you have a prominent radio jet, which is really effective in hitting the halos, are only a small fraction. However, recently it was proposed that you don't necessarily need a radio jet, a highly collimated radio jet to hit the halo. You can do it also via broader quasar-driven outflows, which can still produce a highly hot wind, which in the end can heat the halo again to temperatures of millions of degrees. So, and this is indeed essentially knowingly or unknowingly incorporated in the simulations. And you see this again, the result of one of these simulations from Illustris in this case. And what you see here, is on the top left. Now we are seeing on very large scale. So each of these dots is essentially is a galaxy distributed on cosmic filaments, the gas density. And here you see the gas temperature, and you see that at some point, each of these galaxies produce these bubbles, explosions of hot gas, which are primarily resulting from the accretion onto the central black holes, driving these massive outflows, which hit their circumgalactic mediums. And in the end, you have that most of the circumgalactic medium and the intracluster medium is heated by high temperature and therefore preventing again accretion. Now, these are all models which show that you can actually achieve avoid accretion, but how do you test observationally the lack of accretion? This morning we were discussing how difficult it is actually to trace accretion by using various techniques. It's even more difficult to trace the lack of accretion. Okay. However, we think we have used an indirect method to actually pin down this phenomenon. And this relies again on the investigating the chemical enrichment. You know that metals are produced by the star formation, by the explosion of stars, supernovae, which inject metals into the interstellar medium, and subsequent generation of stars recycle these enriched gas to form new stars. And therefore, what the consequence is that in this cycle, subsequent generation of stars keep being more and more enriched. Okay, and this cycle is, of course, very sensitive to the processes that I just mentioned, because outflows tend to remove metals from the galaxy. Okay, so you can trace this through the metal enrichment. On the other hand, accretion of pristine or near pristine gas from the intergalactic or circumgalactic medium, since you are accreting primarily hydrogen, is diluting the metallicity of the gas. Okay, so you can actually have a proxy of this process to the metal enrichment. And one of the best ways to trace this is by investigating the metallicity of the stellar population in galaxies, which you can do if you have a good enough spectrum. And how you can constrain these phenomena by the metallicity in the stellar population? Well, you can actually get it, but by seeing these cartoons, which show the evolution of the stellar mass and the stellar metallicity in galaxies in the two scenarios. Okay, so suppose that you have a galaxy which is forming stars from gas, okay, and accreting gas from the intergalactic medium. So what you have is that as the galaxy forms stars, so you increase, of course, stellar mass. And since subsequent generation of stars are forming from enriched gas, the stellar metallicity, of course, increases. But does not increase by a large factor, because you keep having this accretion from the intergalactic medium, which dilutes the metallicity. So essentially prevents the metallicity to increase by a large factor. If at some point you have an ejective phenomenon which removes gas from the galaxy, then what happens? Nothing happens. Essentially, you stop star formation, okay, and the galaxy evolves into a passive system, and the resulting quiescent passive galaxy has the same stellar mass and the same stellar metallicity as the star forming progenitor, right? Let's investigate now the starvation scenario. So as long as you have this accretion of gas and star formation, you keep having that the galaxy form, increase the stellar mass and increase the stellar metallicity, not by large factor, because you keep having this dilution effect from the intergalactic medium. if you at some point you isolate the galaxy, so for some reason doesn't the galaxy doesn't receive anymore this fresh supply of gas, and at that point the galaxy is isolated, but it doesn't stop immediately star formation. It still has gas available, so you use the available gas to form additional stars, so the stellar mass increases, and of course now the stellar metallicity increases much more steeply because you no longer have this dilution effect. It essentially is evolving like a closed box. The result is a passive galaxy which has a stellar mass which is somewhat higher than the star-forming progenitor, and a stellar metallicity which is much higher than the star-forming progenitor. So you can explore these two scenarios. So whether you have a metallicity gap between passive and star-forming passive galaxy and the star-forming progenitor is a signature of starvation. And this is what we observe in real data. So these are essentially so it's the same diagram, stellar metallicity as a function of stellar mass. And this is our data, the average of distribution of metallicities and masses from thousands of galaxies from the Sloan survey. Okay, and this is compared with the same quantities in the star-forming galaxy, especially for the progenitors at high ratio. And you see that there is a clear gap in metallicity between the passive and the star-forming progenitors, which is, as I said, the clear signature that the starvation, the quenching of these galaxies has happened through an extensive process of starvation. It's not the whole story. I don't have time to go in great detail, but it cannot be only starvation because it's a more complex issue, but it's simplified in this simple diagram. If you, after the start forming phase, you have the start quenching through starvation, the on long time scales, you still have too much star formation in passive galaxies. And the other problem you are overshooting the metallicity that you see in passive galaxies. At some point, you must have an additional event of outflow which clearly clean the galaxy of the gas content, which can be a sudden outflow event. You may say this is a sort of sounds like an ad hoc artificial event, but actually it's not unphysical. And if you want in the question time, I can discuss that. Or you can have a mixture of starvation and outflow to achieve a lower star formation rate and a reasonable metallicity. Okay, so just to say that it's not as simple. You must have probably a combination of starvation and ejection of gas. Okay. Finally, you want to explore this other scenario of star formation efficiency. This was investigated in the past by some authors and found that there are indeed a few galaxies which, with respect to the Schmidt-Kennecott relation, have a star formation efficiency which is significantly lower. And this actually often associated with the AGNs. It wasn't clear why this is happening. And I think now recent observation, including my own group, seems to shed light on why this is happening. So this is a galaxy again with an AGN, and although even galaxies AGNs which are not really loud, most of them still have weak radio jets. Okay, and this is one of these. And this galaxy was observed in Muse, and so this massive integral field spectrograph at the BLT at ISO. And what you see here is in contours is the radio jet, and in color is the emission of the oxygen 3 nebula lines, which is nicely aligned with the radio jet. Okay, this is nothing new. We know that this is probably gas illuminated by the AGN. Okay. However, the really surprising finding is that the velocity dispersion of the gas, we were expecting it to be highest along the radio jet where the gas is being heated by the jet. And instead, it's completely perpendicular to the jet. So it's actually the maximum of turbulence is in the ISM of the galaxy perpendicular to the jet. And this is in very nice agreement with what was expected by the hydrodynamical simulation of galaxies, including radio jets, so which is shown here. essentially what's happening according to the simulation, while the jet drills into the ASM trying to escape the galaxy, injects a lot of energy into the ASM, and this energy essentially propagates isotropically nearly into the ISM by increasing the turbulence of the circumgalactic, of the interstellar medium. And of doing so, if you increase the turbulence, you suppress the efficiency of star formation. Okay. Of course, these are two galaxies. The question is how often this happens, how responsible, how much this phenomenon contributes to the quenching of star formation in galaxies. And this, so you want to investigate again, back to this diagram where we have star formation rate as a function of stellar mass, how much of this quenching phenomenon, where you go from star formation to passive, is due to the lack of gas, so either ejection or starvation, or to lack of lower star formation efficiency. And to investigate these, so whether it's a lower gas fraction or a lower star formation efficiency, that is the star formation rate per unit gas mass, you have to measure the gas content for a large, if you want to investigate this statistically, for a large number of galaxies. We have used here a trick that is to use the dust absorption to the Valmer decrement, which is an imperfect tracer of gas content, but correlates with the gas content. The advantage of doing that is that although it's not very accurate, you can do this for thousands and thousands of galaxies. And that's what we have done with especially this, my student, Asia Petrovska. And so you, this is the result, essentially the same diagram, star formation rate as a function of stellar mass, where here galaxies are, the distribution of galaxies color-coded by gas fraction, okay, in this diagram, and star formation efficiency in this other diagram. And you see that as you leave, galaxies leave the main sequence, you both decrease the gas content, and you both decrease also the star formation efficiency. So galaxies leave the main sequence and become passive, both for the lack of gas due to ejection or starvation, and for star formation efficiency. So these three phenomena, these two or three phenomena, act together to quench gas. All of them happen in galaxies to produce the passive population. Okay. So this is a scheme illustrating the quenching process, and what we have seen so far on we have seen the mechanisms which are responsible for quenching. So summarizing gas removal or ejecting mode, starvation, and star formation efficiency, suppression of star formation efficiency. And we have seen that essentially all of them in different contribute to the quenching of galaxy. What you see instead on the x-axis, I haven't discussed much, is what is the primary cause of this mechanism. And each of these mechanisms can be produced by different actors. Let's say environment, let's say, as I said, non-pressure stripping, which can remove gas, or in this case, I didn't mention it about strangulation, which is the effect of when galaxies plunge into an overdense region, such as the cluster of galaxy, and get stripped of their circumgalactic medium and essentially become isolated from further accretion. And this phenomenon in this case is called strangulation. Sorry about that, these terms are also horrific, starvation, strangulation, but this is, I mean, astronomers must be sort of with the mind, well, this comes back to my book because it's a thriller, so maybe I'm also part of this mindset. Okay, the starburst, as I said, through supernova explosion can remove gas or heat the stellar medium or heat the halo through these supernova-driven winds. Backward accretion also can, as I said, remove gas, steer the ISM through turbulence, as we just showed, and as I just discussed, heating the circumgalactic halo by ejection of energy via radio jets or outputs. Okay. The question is, and I don't have time to discuss the mass effect, but if you want, you can discuss the question. The question, so you want now to investigate whether there is, all of them play some role or some of them have a dominant role, okay? Certainly all of them, as we saw, do play some role. the question is whether there is a dominant cause. And if you want to investigate that, you need again large sample, because this galaxy, if you investigate the individual galaxy, that might be subject to a sporadic or local event. And so exploring these requires large samples to have enough statistics to overcome the local weather, whatever you say. So for doing that, we have used the manga survey, which is one of the latest versions of the Sloan survey, which essentially provides integral field spectra for 10,000 galaxies. So you have for each of these galaxies spectral information on the 2D. And you can, this is very useful because you can distinguish star-forming regions and quenched regions in the individual galaxies. So this is a case, for instance, of a galaxy which is star-forming everywhere, a galaxy which is quenched everywhere, and galaxies which are star-forming outside and quenched inside, and vice versa. Okay. And what you see here is the same diagram that I showed you a few minutes ago, that is star formation rate as a function of stellar mass, where instead you have the resolved quantity, so surface density of star formation rate and surface density of stellar mass. And you see that even for the resolved quantities, you have a sort of resolved star formation main sequence, and then you have a resolved quiescent sequence, okay? So the question is again understanding try to understand what is the cause, either local or global, responsible for star-forming regions to become quiescent, okay? And with such a sample, you can investigate this in a robust way. And to make a long story short, it seems that the main actor in determining whether a region becomes quenched is the black hole mass at the center of the galaxy, as measured in part through the central velocity dispersion, there is a tight correlation between central velocity dispersion and black hole mass. And you may say, and you see this in this diagram, where essentially you have the same diagram as before, okay, but now color coded by black hole mass. And you see that galaxies in the quiescent region are systematically have higher black hole masses than the galaxy, the star-forming regions which are on the star-forming sequence. And you may say, okay, well, this is really not direct evidence, because black hole mass correlates with everything. It correlates with galaxy stellar mass, with the halo mass, with a lot of other things. Okay, so how can you actually distinguish that this is not simply an indirect correlation? Well, when you have such a high statistics, you can do that, okay, because you can disentangle the various evidence. So for instance, you can plot diagrams like this, where you have black hole mass as a function of stellar mass, color-coded now by, and you do see the correlation that was mentioned between black hole mass and stellar mass, but now you can color-code by fraction of quenched galactic regions, okay? And you see that at the fixed black hole mass, the fraction of quenched galactic region is very little dependent on stellar mass, if anything, okay? So nearly independent of stellar mass. While at the fixed stellar mass, the quenched fraction depends strongly on the black hole mass. Same applies for the halo mass of the galaxy. The quenched fraction depends very little on the halo mass, while it depends a lot on the black hole mass. And you can do the same experiment for a lot of other quantities, bulge to total ratio, metallicity, and so on. The problem is that, of course, our poor human mind struggles to now investigate this color coding in multiple dimensions. Okay, we are certainly limited, and so for doing that, we are starting to use artificial intelligence, which can, with some guidance with machine learning, can actually visualize this correlation in multiple dimensions. And among various tools that we have used, we have used the so-called random forest, which has been extensively used in various studies. And essentially, the random forest, what it does, goes into this multidimensional space and try to identify among various galaxy parameters, both global, such as stellar mass, bulge to total ratio, or local parameters, such as metallicity, surface density of stellar mass, or environmental parameters, such as halo mass, galaxy over density, and so on, and try to identify what is the local, global, or environmental parameter which is primarily responsible for the fact that the galaxy or a galactic region is quenched. And what it finds again is that the black hole mass of the galaxy is the most important parameter which determines whether a region in the galaxy is quenched or not. Okay, so back to this diagram, it seems that the primary actor is the black hole accretion, and especially the integrated black hole accretion, which is the black hole mass. So in terms of quenching, at least, sorry, I forgot to mention, this applies for galaxies which are in the lower density region, the central galaxies, or the massive satellites. Doesn't apply to low mass satellites. I'll get to low mass satellites in a minute. So in the case of central galaxies or massive satellite galaxies, black hole is the king or the queen. I don't know what is the gender of the black hole. Anyhow, it's the ruler. Okay. If you go to instead to low mass satellites, is actually is quite different, and you see now is the same kind of diagram where the light colors now gives the importance of these various parameters for satellite, low mass satellite galaxies. And you see now that the black hole mass has the minimum low importance, while the galaxy over density traced by this delta 5 parameter is the most important parameter. Okay, so in this case, for low mass satellites, the environment is king or queen. Again, I don't know what is the gender of the environment, but and therefore what plays a role for low mass satellites is round pressure stripping or this effect of strangulation that I just mentioned. Okay, so going back to this overall scenario, I think that I can summarize based on what we have found. We can summarize the galaxy quenching in by saying that there are a broad range of causes, of mechanisms and causes, but we can say that for central galaxies and high mass satellites, the integrated effect of black hole accretion, that is eventually the black hole mass, is the main culprit for killing galaxies. All again for using these disturbing terms. So what's happening likely is that quasar-driven outflows do hurt the galaxies by removing, cleaning the galaxy of a large fraction of the dust, but actually this is not enough for quenching. Most of these outflows escape the galaxy to the least resistant paths, and go into heating the halo, and this halo heating results into preventing the cold accretion to the galaxy and therefore starvation. On top of this, there is also an effect of reduction in star formation efficiency, which also contributes to the quenching of the galaxy. Instead, for low mass satellites, what's happening is that the key effect is environment, and primarily due to the fact that galaxies plunging into overdense regions get stripped of their circumgalactic medium, and therefore they don't are essentially prevented from accreting additional gas, and they die by starvation as they wander into these dense regions. And if they go into the inner regions where the gas is particularly dense of the intragalactic medium, they get suffer also from ground pressure stripping. Okay, so I think how am I doing in terms of time? Okay, I'll just wrap up by saying essentially the future prospects. Okay, so then maybe you can wake up with this forward-looking perspective. So most of what I have shown is based on local studies. However, most of the quenched galaxies locally are very old. Okay, so although we trace these effects locally, but the bulk of the quenching, since these galaxies, the quenched galaxies are old, must have happened long ago, around 10 to 13 million years ago, billions years ago. Okay, so you want to explore this quenching mechanism in action back in time at high redshift. And so we have a program to investigate that, and in particularly for investigating this phenomenon of halo heating. This is very tricky because if you want to explore the heating of the halo at high redshift, in principle, the best way would be with imaging these galaxies with X-rays and see the X-ray emission from the halo. But this is completely out of reach of current facilities. Maybe with Athena in 10 years will be possible. But it is actually, although challenging, within reach of millimeter sub-millimeter facilities with the scenario of the effect. That's the effect you may know is the effect of scattering the CMB photons to higher energy, and therefore, when you image galaxies, clusters of galaxies or halos, hot halos against the CMB, you have a suppression of signal at low frequencies and increase at high frequencies. And there have been several studies which have used CMB experiments by stacking the signal from thousands of the line of sight of thousands of quasars, and by doing so, they have found a technical indication of the signal that is there is hot halos around quasars. However, the problem here is that the beam of CMB experiment is so large that includes emission of the quasar itself, of the satellites around the quasar. So it's a very difficult experiment. Okay. What you can do, however, with ALMA, you have the sensitivity and the resolution to actually detect the effect, although it takes a lot of hours for integration, and actually also isolate the emission of disturbing quasar or random galaxy. This is a simulation by a student of mine that this is actually doable, but you need several hours of integration. But we have now a program in Cycle 8 with about 50 hours of observations, specifically aimed to detect this as the effect at different redshifts. So this is, stay tuned because this may be a very interesting way to detect this phenomenon. The other way we are using ALMA is to detect, again, cold outflows in distant quasars. This so far was detected only for a few quasars because, again, these high velocity wings are very weak, need a lot of integration, and it will require sometimes stacking. So we are actually, again, the same program is also exploring these high redshift cold outflows. And then, of course, we have James Webb, hopefully being launched in a few weeks, and hopefully after deploying, delivering fantastic data. And here, of course, the revolutionary aspect is the sensitivity, especially in the spectroscopic mode. We are talking about, in some bands, in a leap in sensitivity of 2000. 2000, I don't know if you have an idea of the magnitude of the leap. Sometimes it's nice to compare this leap. I like this similitude that is equivalent to suddenly, in the optical, suddenly passing from Galileo's telescope to modern GTC or VLT telescope. So this kind of, so you can think of 400 years of discoveries unleashed in a few years of observations. And of course, with James Webb, you can explore the ionized outflows because most of the optical nebulous lines are shifted into the near and mid-infrared, and this is a simulation of a redshift 6 quasar, the early chemical enrichment, and also tracing the emergence of the first passive galaxy, which currently is nearly impossible with ground-based instrumentation. And then the other instrument, which I think will be in this context quite revolutionary, is MOONS, which is the next generation optical near-infrared multi-object spectrograph for the Very Large Telescope, which is currently under construction and will see first light in a couple of years. And essentially, it's an instrument which can obtain 1,000 simultaneous spectra in the optical and near-infrared. And with this kind of multiplexing, you can actually obtain, in a few years of observation, nearly 1 million spectra for galaxies around the cosmic moon. And this is the kind of statistics that you need to trace large-scale structures, and not only the environment, but also the properties of galaxies in these large-scale structures, and therefore explore the role of environment in quenching galaxies at the epoch where this effect is supposed to be most important. Okay, and I just finished there to say that this is one kind of a topic that we are exploring in chemistry, but there are many other things as we discussed in the past days, such as chemical enrichment, dust, and and the dynamics of galaxies that I'm glad to talk with you in later today or when next time I visit. But I just want to thank again Ignacio and Christina for inviting me and hopefully coming back for a longer visit. But I also want to reverse the invitation and hope that some of you can visit us in Cambridge, depending on the pandemic, both faculty, but also students and postdocs. We have support for it, supporting visiting students and junior postdocs. And so I encourage you to get in touch with me if you want. And we can, I've seen in these days that there are a lot of commonalities and common interests and connections that can be very productively developed further. So I'm really looking forward. Thank you.
Thanks a lot. We're first starting with the questions in the aula, and then there's at least one question by John Beckman.
Oh.
So, we first question here. Do you mind? But then people continue. Thank you for the talk. It was very interesting, Professor. Grabbing a bit of with your last slide about the environment, it seems to me that these studies were a bit more focused on the galaxies that are in dense environments such as galactic clusters. But what can you say anything about these galactic transformations in, for example, field environments where we don't have much more a massive concentration of galaxies?
Well, yeah. Actually, it's not true that we are focusing on classes. Actually, if I go back to actually in manga, unfortunately, fortunately in this case, cluster environment, the very dense environments are underrepresented because they are not. It's not suited manga to actually probe much cluster environment. Most of these delta 5 measurements are actually in a very broad range of environments from, yes, some classes, but mostly groups, filaments, and so on. So actually, this is actually probing a broad range of environment. And the previous, there is another work by James Pastor, a former student of mine, that actually used this Sloan to investigate this effect in a different way. And I can give you the reference, but there, we span orders of magnitude in delta 5, so from dense clusters to all the way to voids. So this kind of statement actually applies to broad range of kind of environment.
So again, thank you very much for this quick overview of the state of the star formation. Formation of galaxies in general, star formation particular. So I have a question, or I have several questions, but I'm not going to make them all. It's about your way to separate between whether quenching is produced by outflows or by starvation. And you show in one of the transparencies a plot of metallicity versus mass for quenched and star-forming galaxies. And the question is that I think I understand the way you propose to do the separation. Yeah. But how are you gonna disentangle the dependence on the age of the stars and the metallicity? Because,
Yeah.
I mean, this stellar metallicity probably very heavily weighted by luminosity, right?
Yeah, no, but this is, I mean, of course, we have time to go into these kind of technicalities, but in this work here, Cluster 2019, there is the full treatment of just what you are saying. We are basically both light-weighted and mass-weighted metallicity and ages. We use actually to infer these, the fact that you actually can't strictly disentangle starvation by, you can only say that starvation plays a role, but as I said, in the end, you need also output, because when you combine all the information that you have for this galaxy, that is metallicity, age, and star formation rate, then you start to actually have to fit all of these phenomena together. And that's why how we came out that you must have a combination of all of these. But it's exactly what we have investigated more in detail in this is it for something like 30 pages paper. It's just we want to make sure that we exactly address specifically what you're saying. The full answer, I mean, would be another seminar probably.
Hi, very interesting talk. I had actually a question on the project for conditional Seldovich effect around at around redshift 3 more or less. So I've been working on quiescent systems, which start to develop at around that epoch more or less. And I was interested into, so we had recently, this past 2 weeks, a very interesting school on photocluster environment. So I was actually thinking, well, actually asking down to which halo masses you would expect to go with such an experiment, because one would think that at the different halo masses you might expect different heating of the halos. So I'm thinking about the Decker plot where you might have cold accretion onto a hot environment.
Yes. Well, first we are going to different ratios. We have 3 programs going from 1.5 to 6 actually. Each of them has different kind of expected sensitivity to the. Now I don't have a specific answer for the whole thing. I should go back into our calculation. But keep in mind that our goal here is not to think in terms of halo masses, because when you think of heating associated with halo mass, you essentially are associating the heating to gravitational shock heating, which is another phenomenon from what we are investigating here. Here we attempt to investigate halo heating by AGN feedback, which is heating injection of the energy by the quasar. In principle, this is totally disconnected by the halo mass. It is in the end probably connected, but as a consequence of the coevolution of the black hole and halo mass. Okay? But we didn't, how to say, submit a proposal with the specifically intention of probing different halo masses, because this has been done by different kind of studies where I focus more on clusters, because that's where we indeed have best chances to get. But it was the focus of the here is to connect the halo heating with the quasar activity.
Thank you.
Hola, Roberto here. Excellent talk. I also have a question regarding the Sunyaev-Seldovich experiment you do with ALMA. So I didn't get it completely. Did you already did a pilot study and you could show that it's possible? So do we have already a detection?
So yeah, this is essentially there is already a study it was a study by Lacey, and then followed up by a reanalysis by my student Sim Bolton, which is a tentative to detect these in on the most luminous quasar ratio 1.5, and you get the 3-4 sigma detection, so very marginal. But the mistake of not the mistake, the naive approach of these studies was to go in band 4. Sorry for the technical, but band 4 is where you have the minimum of the scenario object factor. So naively, people have targeted this region. However, doing so, you don't take into account by other technical aspects with ALMA. That if you want to explore the scenario Zadovich, this is a signal on very large scales. So you have to follow the strategy with the capability of being sensitive to very large scales. And what Sim, my student, figured out by doing leveraging on this result, doing simulations with ALMA, is that you are much better off by doing this kind of observations in band 3, so the lower frequencies, where the depth is somewhat lower, but the sensitivity of ALMA is much better to large scales, but because you have a larger field of view and the beam is larger. So the approach of all of these programs that I mentioned is actually now to go for a long integration in band 3. And there is, according to the tentative signal that you have in band 4, you should get far better signal in band 3 because of these technical aspects. So so there is, if you want, a pilot, but the pilot has demonstrated that the previous stuff was wrong, sorry, inappropriate. Okay.
Okay, a quick technical question to this program. So this is only ALMA 12 emitter array, or
It's
also
both. You have
ARCA?
both 12 and ACA, and actually the ACA are nearly already completed. We have got last night notification that this is nearly done, so you should get some ACA results soon.
Okay, thank you, Professor. Very impressive result. I would like to ask if the formation of brown dwarf could contribute possibly to the quenching of star formation process, especially in the starvation process, because formation of brown dwarf and formation of star, they compete each other, and there are more brown dwarf than stars according to our knowledge, according to the initial mass function. And from the billions of years ago, the brown dwarf forms, and till now the brown dwarfs are full star, and we are not able to see them. Is that a possible?
Could be essentially. That is an interesting perspective. I cannot give certainly a straight answer now because I think this has never been well, as far as I know, not the closest kind of analysis that I can think of is to about variations of the AMF as a function of different class of galaxies, where you essentially tend to be more low mass weighted, and it's an interesting perspective actually. I don't know if this in the end can actually have a minor or major effect on what we define as quenched galaxies or not, but it's a good question. I don't have a straight answer, but I think there are already some data which one could use to try to investigate this. It's a good point. No, I don't have a straight answer, by the way.
Thank you.
You want to ask the question yourself? Thank you very much, Roberto. You didn't, I mean, when you discuss the bimodality in the local universe, you discuss the bimodality in star formation, but there's also a bimodality in galaxy structure, stellar morphology. So you didn't say anything about that, but how
that was the part that I initially said I wanted to also incorporate that, but
can you say a word about what these mechanisms? I mean, if there's a morphological transformation or just stating that's happening, what's the take on that?
Yeah, there is certainly, well, initially, this has been discussed at length, whether the morphological transformation is just apparent in the sense that the disk, suppose that you have the starvation scenario, you stop star formation, the disk, which is prominent in star forming galaxies, fades, and you get a more prominent bulge, so the classification gets more spheroidal. However, these I got convinced by Michele Cappellari, who is leading this area, and also by our own studies. It is not only about fading and morphological aspect. You have a clear difference in terms of dynamics. So the quenched galaxies tend to have, at least above a certain mass, different dynamics with it. It's not totally true at low masses. When you go to low masses, let me see if I have a diagram here. When you go to low masses, you have a lot of, I have yet another paper by another student which is investigating exactly this, the dynamics as a function of quenching. And essentially, especially at low masses, you have the same kind of dynamics. You have essentially have the fast rotators, what Michele Cappellari called the fast rotators, and essentially you can explain those as sort of the fading of this. But as you go to higher masses, you clearly have a higher fraction of different dynamics. And now the question is, so there is a real structural difference, which is probably, and the question is to understand whether that's a driver or a consequence, or an indirect effect. I'm prone to, how to say, based on what we have found, especially this last study, which is yet another 30 page, which should appear in archive in the coming weeks. It's not my fault about this 30 pages because the fault is where is Asa Black, who is a postdoc in who is now a faculty in Florida, but he likes to explain everything, and so we end up with these 40 pages. But it is good, but in the end you have few people reading them because they get discouraged. But anyway, sorry for the digression. So going back to the point, I think although this has to be explored further, I think is an indirect byproduct in the sense that what happens is that in the massive galaxies, you do have the merging which affect the morphology and the dynamics. And these also affect the black hole accretion, which I suspect is the factor which is responsible for heating the halo in the end and responsible for starting the galaxy. And now you do have the correlation between morphology, dynamics, and quenching status, but this to the black hole, which is the prime actor, and the structural transformation that you have associated is a parallel byproduct. So that's, but I still need some exploration. Okay.
Nobody else has a question. I have a question myself, and maybe tell So, keeping a landscape and how you see it works and how the equation works in the nearby universe, now, with future facilities, maybe we will be able to go more distance getting close to the landscape. You expect, one would expect, or we may know, that the population of massive black holes might be different. So we expect that this quenching mechanism would be different as
could very well be, and that's why we want to explore these, especially with James Webb, but also with Alma, as I mentioned, we have a program to test these at Redshift 6. So that's essentially reionization, close to reionization. And James Webb, most of our GTO program is around Redshift 6, and that's what we are going to explore in detail. Yeah, could very well be, who knows? Yeah.
Yeah, should I read it? Yeah, there's a question. So John Beckman is asking, how do the considerations you have dealt with in this talk produce the monotonic entitlement between central black hole mass and bulge mass in normal style? And if black holes are quenching, one might expect a negative correlation between black hole mass and bulge.
Yeah, but this is exactly what we have explored, because this is where was it? Wait a second. When you have such large statistics, you can disentangle these various effects. So here, for instance, we have included both the black hole mass, but which is proved by the central sigma, okay, which is something that you can argue, and disentangle from the black hole mass. You see here. So if you again, sorry, the bulge mass. Again, if you have few statistics, you can't do that because and everything is linked, and so you don't know which is direct, primary, and secondary. In this case, with such large statistics, you can clearly see that the black hole mass, the bulge mass, is a secondary effect, as we did in this other case where we can actually, again, these all are all connected, but you can disentangle the contribution of the two. So we think that we have solved that degeneracy. Now that's another story. If then you think that here this connection is not you're relying on a relation, but if you want, I can show you another slide on that.
Yeah, I had a comment on this that I told several times. I think random forest is the idea of breaking the degeneracy because the parameters are correlated. Then the result might be misleading. But I think he answered me something I don't remember the answer. He made some sense.
Okay.
But
there is also if one one is down about the correlation, there is also the direct, how to say, black hole measurements, which can be used to test these. Let's see. Here we go. The direct, and in this case, so you can, so in this test, since when you have 10,000 galaxies, you can only rely on the proxy as the central sigma to measure that one. But these are the same kind of analysis where you use the direct measurement of black hole mass to nuclear dynamics with maser and I mean, go very solid. And you find the same result. For instance, here you see that the fraction of quenched is nearly vertical. It depends on the black hole mass and not on stellar mass. But now you have a statistics of 100 galaxies, maybe 50, so the assessment is less solid. But it's reassuring that when you go with the velocity, central velocity dispersion, this correlation is very tight. So I mean, it's reassuring in using this proxy as a local mass the largest stuff.
Another question by James, asking about the black hole quenching again, and the correlation seems that it doesn't hold for the small stellar black hole mass. So, less massive galaxies or more.
Yeah, well, there.
I mean, the black hole is less.
Do you mean this plot here?
Probably.
Here. Yeah, here there is a problem. You don't see very well because of the projector, but you see this shaded region here. This is essentially where the black hole masses are not really trustworthy because leaving aside the calibration of this correlation where it falls down to low masses. The main problem is that here we're using manga data which have a resolution of 2000. And so you can't measure the velocity dispersion below sort of 100 kilometers per second. So at some point, essentially, you don't have any more the capability of disentangling the error. So one should is a work for anyone who is interested. I mean, we are running out of people doing this. So if you're interested, to actually use other surveys with higher spectral resolution and go further down in exploring the installation. So it's, but with this only we are limited by the spectral resolution.
No,
No,
we have a
fine.
couple of extra questions. Raise hands, so I don't know if you want to open your mic and ask a question. Pablo, from Madrid.
Hello. So hello, Roberto. You did a very nice review of all the possible murderers of the star formation, and you even came up with the king, the supermassive black hole.
Or queen, don't.
Queen. Yes, okay. But you didn't mention two concepts. I don't know if because you don't feel they are relevant. The first one is resuscitation and the consequent rejuvenation. So if galaxies do excursions in and out of the main sequence, or they just die forever. That's the first concept. And the second concept, I don't know if it was covered by the last question in the room because I couldn't hear it very well. And it's the dependence on redshift. It's not the same having a 10 to the 10 solar mass galaxy, a redshift of 4, where you have a lot of gas, that when the AGN were very, very active, maybe even the IMF was different, and probably the environment was not a relevant actor at all, than having a 10 to 10 solar mass galaxy at redshift 0.4 or something like that. So things can strongly depends, quenching can strongly depend on redshift, and what we learn in the local universe might not be exactly what is happening at high redshift.
I absolutely agree. I'm fully on the same page, and that's why we are expanding with moons and ALMA and other facilities to higher range, because we want to see how these all of these kind of studies that we have done mostly locally evolve, if anything, like higher redshift, to see whether the quenching processes actually play a different role at different redshift. Okay, so particularly the environment, for instance, we know the environment, most dense systems form below redshift 1. So do you expect that? Probably we expect the environment plays a lesser role at higher redshift. Okay, and so that's exactly what we are going to explore with moons, by essentially doing the same Sloan survey, but at redshift between 1 and 3. Okay, so this is certainly an open area of research which you're absolutely right, and we want to explore. About the rejuvenation, yes, that's also a very good point. In particular, rather than fluctuation around the main sequence, which is, for me, is more about weather, but essentially what happens that a galaxy which is close to being passive and quiescent gets rejuvenated by an accretion event, which can happen. I think Ignacio explored these. What is Ignacio? Sorry. And I think this is certainly happened for a number of galaxies. But I think, as also Ignacio has pointed out, these may still be part of the quenching process, in the sense that whenever you have a rejuvenation phenomenon, you don't not only have some more stars, because the rejuvenation again in terms of mass is not a big deal for the whole galaxy, because the galaxies have already acquired a lot of mass, but it can inject a lot of energy to supernovae and through additional black hole accretion that is feeding the black hole. So that's also another aspect that is the additional complexity of this whole process. And actually, we have another, I would say, thread of research, which is actually the effect of positive feedback. Okay, so which I totally ignored here, but is I sometimes give an entire seminar about this other aspect, that is positive feedback, and which is actually the effect of AGN outflows, for instance, in boosting star formation. And the main point that I have discussed with my colleagues, simulators, and so on, is that even this positive feedback that AGN accretion, for instance, can have, in the end, results into a negative feedback. Because, for instance, one of the things that we are extremely excited about, that we have found in very recent observations, and which I can show you if you want offline, is that in some of these outflows, you have a lot of dense gas, which is outflowing, and it's actually forming stars. The nice thing is that the stars which forms on these outflows essentially explode as supernovae in the halo. And this is fantastic, because the problem of the reason why the supernovae in the galaxy, in the interstellar medium, are not very effective is because most of the energy is quickly lost as a consequence of shocks in the dense interstellar medium. So that's why most simulations do not get much negative feedback from supernova. But when the supernova explode into the halo, they are free to essentially couple entirely with the halo and release all the energy into the halo. So they contribute a factor of 1 or 2 orders of magnitude more to the heating of the halo. So you see that also this rejuvenation or positive feedback in the end helps with the quenching in some way, in particular in this case via starvation. So I have unavoidably oversimplified everything here, but if you want, I can give you yet another seminar on these other aspects. Okay.
I think a very, very last question by Alexander Vazdekis. I don't know if you want to in your mind.
Yes. Well, it's in fact, it could be in continuation of Pablo's question to some extent. Yeah, regarding these different murderers of the star formation, if one consideration I would like to make is that, well, we have been working already for a while on the two-phase galaxy formation scenario for massive galaxies, where in the one of the characteristics of the first phase is that we have a top heavy IMF that evolves toward the bottom heavy IMFs afterwards in the second phase that extend to nowadays. So the point is that I do see the top heavy IMF scenario that is sort of transversal to all the possibilities that you pointed out in your wonderful, by the way, slide. It could work at, for example, ejecting gas outside. Of course, more difficult in a massive galaxy to some extent, but at least extends to larger masses than if you assume just a standard IMF. And also it works on the starvation. Why not? I do see it quite reasonable. And of course, in the latter one. So, how do you see this within that, let's say, possibilities?
No, it's absolutely completely agree that we have, at least in this empirical, empirical approach, we haven't considered the variation of the DMF simply because we don't have a proxy for that. Okay, but it makes total sense that if you have a top heavy MF, of course, the energy that you inject either in the SM or in the CGM per unit stellar mass is far higher, and so that helps a lot with the overall quenching. And so yes, that can be another aspect which, as you say, is transversal to all of these aspects. It can help with the ejection, with the starvation via heating, and also in terms of efficiency of subsequent star formation, because
exactly
you inject turbulence and heating into the working all of these scenarios. So yes, this is the problem is that how to say, it goes back to the question that I had a few minutes ago. Is more tricky to test because you don't have an easy proxy of the MS on large samples. Well, now actually there are some groups which are attempting that, so maybe it's something that can be explored, but it's not as easy as in these cases where we have relatively solid quantities which we could play with and distribute in multiple, manipulating different statistical way to disentangle different definitions. So, but it's something that can hopefully be attempted with some recent analysis that some group have done in attempting to constrain them. That's simply something to do. Yeah.
Okay. So thank you very much. I think we